Oh, welcome. Welcome to our UChicago Space Talk on two new UChicago-led experiments to discover the highest energy particles in the universe, featuring star cosmologist Abigail Vieregg in conversation with the UChicago Space Network. My name is Josh Levitt. I'm an alumnus of the college and a development professional supporting UChicago's research, teaching, and learning in the Physical Sciences Division. It is my pleasure to turn this conversation over now to Dave Fischer, a fellow alum who leads the UChicago Space Network, a community of scholars, entrepreneurs, and enthusiasts of astronomy, astrophysics, and aerospace. Go ahead, Dave.
Awesome. Hey, thank you so much, Josh. Welcome, everybody. I'm Dave Fischer. I lead the University of Chicago Space Network, which is an alumni community, and it's intended to connect everybody who's associated with the University of Chicago. So alumni, as well as current students, others who are interested in space. And when we say interested in space, we mean both interested in space as a scientific endeavor and as an area where business is done. There's been a really flourishing growth in the space economy in recent years. And so we're also very pleased to bring together a lot of people in the community who are parts of this growing space business community. We will put in the chat some links to our LinkedIn page and to sign up for our newsletter. We would love for you to be engaged with us if you care to be. And with that, I will introduce Abigail Vieregg. She is the David N. Schramm Director of the Kavli Institute for Cosmological Physics at the University of Chicago and a professor in physics and the astronomy and astrophysics departments, as well as the Enrico Fermi Institute. As we'll learn more about today, Professor Vieregg builds radio and millimeter wave experiments and uses them for neutrino, astrophysics, and cosmology with cosmic microwave background. A huge topic and really exciting science. So Abby, I'll turn it over to you.
Sounds great. Let me share my screen. And hopefully that looks right on your end.
Yes.
Is that true? Good. Okay. So yeah, I'm really happy to come and chat with you at lunchtime about the research that my group at UChicago is working on. As you mentioned, I have interests that are sort of broad in experimental particle astrophysics and cosmology. So I've worked on a variety of experiments, but today I'm going to tell you about two experiments that are just sort of getting off the ground right now and are a bit forward-looking. And the goal of these experiments is to discover the highest energy neutrinos in the universe. Okay, so the picture on the front page is actually a picture of a place called Summit Station in Greenland. So Summit Station is right in pretty much in the middle of Greenland at nearly the high point in the plateau. And the National Science Foundation runs a research station there. And until we first went to Summit Station in 2013, most of the science that was done there was atmospheric science, science related to snow and ice, and a lot related to climate change. But now Summit Station does astrophysics. So I'll tell you about how that happened a little bit, and then I'll talk about another project that we are working on that is a NASA long duration balloon project. Okay. So the first thing I have to tell you is what is a neutrino. So if I'm going to talk about why we are going to look for ultra high energy neutrinos, first we have to talk about what a neutrino is. So neutrinos are a fundamental particle. That means that they can't be broken down into smaller pieces. They are abundant. They are the second most abundant particle in the universe after photons. They are elusive, meaning they are hard to detect. Many neutrinos are passing through you right now from the sun in particular, from our own atmosphere actually. And I was just gonna see if I can mute. There's something.
I'd like to ask all the participants to mute. I think we're getting some background noise, please.
Yeah, Dave or Josh, I think you can probably do that also, actually. Okay, so neutrinos are abundant. They're the second most abundant particle in the universe, or photons. They are elusive, meaning they travel right through you most of the time without interacting. They can, so that is a really cool feature of neutrinos, because what it means is, it means that they can travel really far through the universe, carrying information about really far away sources, which is a characteristic that we use in our research to learn about distant sources in the universe. Neutrinos are oscillating. This is a characteristic that's a little more in depth about particle physics, but it actually turns out that neutrinos come in 3 flavors. That's what's shown down here in the lower left. Neutrinos come in 3 types. And as they propagate through the universe, they oscillate from one to the next, which is pretty incredible. Like, you can start having made one kind of neutrino at some source and then measure it later, and it then turns into the other kind of neutrino. And they're lightweight. They're really low mass particles, which is also an interesting feature about neutrinos. So one of the things that I want to get across is that we can use these really cool particles as a tool to learn about, well, particle physics, you can imagine, right? But also astrophysics. So neutrino astronomy has a brief but important history. And when I say brief, I don't really mean brief over time. I mean that there haven't been that many sources seen in the light of neutrinos. The first source outside of the Earth and its own atmosphere that was seen in the light of neutrinos was the sun. This was first observed in the 1960s by an experiment that eventually won the Nobel Prize. And the reason that it won the Nobel Prize is because they went out looking for neutrinos from the sun. And it turns out that you can try to calculate, based on astrophysics, how many neutrinos should be coming from the sun. So the reason neutrinos are coming from the sun is because of nuclear fusion. So when the sun creates heavier elements, neutrinos are produced. So they're produced all the time in nuclear reactions. You can calculate the rate at which this should happen from the sun. And then you can build a detector and go try to measure these neutrinos. So this is what a group of people did. And it turns out that the rate that they measured was a factor of 3 lower than the rate they calculated. So either this means there was a problem with astrophysics, or our understanding of how the sun works, or our understanding of nuclear processes, or there was something else going on. And it turned out that the something else that was going on was that neutrinos were oscillating. So I already talked about this on the previous slide. You can make one kind of neutrinos, and in the sun, you make electron neutrinos, because that's the most, in nuclear processes, that's the kind of neutrino you tend to make, because electron neutrinos are made when there's electrons, and there's electrons in regular matter. And so, then the electron neutrinos oscillate, they come to Earth. And when you try to detect them with your experiment, that in this case was only able to see electron neutrinos, they've turned into a different kind, and you can't see them with your detector. So that's what happened. That ultimately won them the Nobel Prize. The second source that has been seen in the light of neutrinos was supernova 1987A. So in 1987, a supernova went off in nearby our galaxy. So in a large the Large Magellanic Cloud, which is close to our galaxy. And we basically just got lucky. So supernovas go off occasionally. The rate is supposed to be something like once every 400 years in our galaxy, although once every few hundred years in our galaxy, although we haven't seen one for a while. And we basically just got lucky that the supernova went off close enough by that we could do really cool things actually by measuring neutrinos that came from this supernova. One of the things that we did by looking at those neutrinos was to place constraints on the neutrino mass, actually. So you can calculate based on the time delay, believe it or not, the time delay between when neutrinos arrive from the supernova and when light arrived from the supernova, how massive the neutrinos are, because the more massive they are, the slower they go. And so that time delay tells you that, allows you to put a constraint on the neutrino mass. So anyway, that's sort of a long-winded way of saying that although 2 sources have really only been studied in depth in the light of neutrinos, we actually learned a lot about particle physics itself, about astrophysics, about neutrino production in stars. And you know, you'd like to imagine sort of what if we could do neutrino astronomy, where we could see many different types of sources in the light of neutrinos, what could we learn? So what so there's an experiment called IceCube at the South Pole. Okay, so all the way at the bottom of the Earth, right at 90 degrees south, there's this experiment called IceCube. IceCube is a cubic kilometer, that's why it's called IceCube, cube for cubic kilometer detector. What it does is it looks for neutrino interactions in the ice. So neutrinos come from some astrophysical source, they come to the Earth, and when they interact in ice, they make a particle shower. And this really big detector, IceCube at the South Pole, has essentially put very sensitive light detectors, so something called photomultiplier tubes that basically take, it turns a very small signal into a big signal that you can detect, and put these photomultiplier tubes all the way down into the ice to make a cubic kilometer instrumented. So if any neutrino interacts and makes a particle shower deep in the ice, they'll be able to see it. This is, to my mind, an incredible feat of engineering. I mean, I can tell you about this and maybe it sounds like, oh yeah, of course they did that. But really, you should be thinking, this is incredible. They, you know, at the South Pole, which is really hard to get to, a group of scientists built, you know, this detector that has 86 2-kilometer holes drilled in the ice, and then lowered strings and pressure vessels with these very sensitive detectors down the hole. And then it turns out it's been running very stably for years and years. And IceCube has been a very successful experiment. So IceCube was built to discover astrophysical neutrinos. So it was built to discover neutrinos coming from sources in our universe that are not the sun or a supernova that happens to go off nearby, but sources that are farther away in other galaxies. IceCube did this in 2013. So in 2013, they published the first discovery of neutrinos coming from other astrophysical sources. IceCube has also done a few other really cool science things over the years. One of the things that I really like is this idea that not only can you measure neutrinos coming from astrophysical objects and try to then learn about what is the central engine that's driving the acceleration of those particles, meaning like what is the physics inside of those sources. You can also use neutrinos in concert with other observations to make an even more powerful measurement. So neutrinos aren't the only thing that comes from other astrophysical sources. Normally, we look at astrophysical sources with regular telescopes where we look at them and we look at different wavelengths of light coming from those sources. Or maybe you look for charged particles called cosmic rays coming from those sources. Or if you're even more clever, maybe you look for gravitational waves coming from those sources. So you could combine, you know, information from neutrinos, gravitational waves, cosmic rays, and different wavelengths of light to maybe paint an even more complete picture about what's happening inside of those sources and how those particles propagate through the universe. So IceCube made the first measurement just a few years ago of a neutrino observation in coincidence with a gamma ray flare. So there's a source, you know, that has some catalog number, you know, it's a TXS0506, but you don't need to know that. There's a source that's called a blazar. So a blazar is an active galactic nucleus. So an active galactic nucleus is a black hole that's accreting matter at the center of a galaxy. And those AGN can spit out jets of particles. And if the jet of particles is aligned in our direction, just happens to be aligned in our direction, that's called a blazar. So it's a source that emits jets of particles aligned in our direction from black holes accreting matter at the center of galaxies. Okay, so there's this blazar that flared. Sometimes that jet of particles gets a little more bright, okay? And when that happened, we saw neutrinos in IceCube. So this is kind of a cool observation where you can use neutrino astronomy and the information you get from neutrinos and also regular photon astronomy. In this case, it's gamma rays, which are very high energy photons, to learn about what's happening in that source. Okay, so that's great. IceCube exists. but I'm an experimentalist, and I like to think about how you can build an instrument to do something no one's done before. So we're not going to build IceCube again. Instead, we're going to build an instrument that goes to higher energy than IceCube. So IceCube discovered astrophysical neutrinos, but it turns out that different sources in the universe make different energies of particles. Some things in the universe are very energetic and make really high energy particles. Other things make lower energy particles. IceCube is only, and that's sort of what's shown here. This is, I think, one of the only plots I'll show you. So the x-axis is energy in a funny unit, and the y-axis is the number of particles also in a funny unit. Okay, so IceCube is sensitive to what I think of as lower energy neutrinos. So the sort of white part of this plot is the energy range that IceCube can see neutrinos in. And in fact, the pink dots are the sort of high energy analysis from IceCube. So this is kind of where they've measured neutrinos. Also on this plot are actually different kinds of particles. So we've seen gamma rays, so that's high energy photons, all the way sort of up to a TeV or a few TeV, that's right here on this plot. And then we've also actually measured high energy cosmic rays. Those are charged particles. High energy cosmic rays we've measured all the way up here on the right-hand side of this plot, all the way to the very right-hand side of this plot, which is 10 to the 20 eV, an incredibly high amount of energy in a particle. It's a funny unit, so the only analogy I can give is that 10 to those particles all the way on the right-hand side, these really high energy protons that an experiment called Auger also formulated and led out of UChicago many years ago, saw particles all the way up to 10 to the 20 EV, and 10 to the 20 EV is the energy that's contained in a fast pitch baseball, except this is the amount of energy that's, you know, collapsed into one tiny proton, right? So you take all the energy in a fast pitch, kinetic energy in a fast pitch baseball and shove it into one tiny proton, and that's an extremely energetic particle, right? Imagine I don't know how many protons are in a fast pitch baseball. I suppose I could try to calculate that quickly, but I wouldn't be able to do it quick enough. Okay, so there are particles all the way out to the highest energies that we've seen, but IceCube, this neutrino experiment, isn't sensitive all the way out there. So what we'd like to do is build an experiment that gets to the pink range on the right-hand side of the plot. So we're trying to think, like, how can you discover neutrinos all the way out to the highest energies? Because we think they should be there. We think that, you know, although IceCube has only measured astrophysical neutrinos up to sort of the center of this plot, we think this flux of neutrinos should just continue to go to higher energies. And in fact, we have reason to believe that even more neutrinos should be made at those high energies as a result of the charged cosmic rays propagating through the universe. Actually, they should make neutrinos as they do that. So we have a source of neutrinos we'd like to look for at the highest energies, and the underlying sort of science goals are to figure out how these particles are accelerated. We've seen charged particles at the highest energies, but the problem is that you can't just take your high energy proton and turn it around and ask, where did this come from? And the reason is because we're sitting in a galaxy, we're sitting in the Milky Way, there are magnetic fields in the Milky Way. And so if you send a charged particle through the magnetic fields of the Milky Way, it scrambles up the direction. So you can't figure out where it came from, right? So ultimately you need another type of particle at the high energies, not just protons, to figure out what is happening at the sources. And it turns out that I would argue that neutrinos are the best way to view the ultra high energy universe. Neutrinos are the only particle that points back to where they came from because they're not charged and travel unimpeded through the universe, meaning they can come from very far away. I mean, the other particle obviously that points back to where it came from is photons, but photons at these high energies scatter off of dust. And they don't make it here. So you don't see photons from really far away, really high energy sources. So we're kind of stuck with neutrinos if we want to look at things like active galactic nuclei at the highest energies in other galaxies. Neutrino telescopes, I think about it that they really open a unique window into the universe because of this property, that they allow you to make the highest energy observation of extragalactic sources. They allow you to look at very distant sources. So you can kind of ask cosmology questions. You can ask the questions like, how did the universe evolve, essentially? Not just questions about like each individual source, but what does the ensemble of sources do as a function of the evolution of the universe? Like how did stars and galaxies turn on and become high energy engines? And then there's the sort of more microscopic question, okay, microscopic rather than cosmology, the more local questions, which are how did the particles get accelerated in each particular source? Okay, so we'd love to build a high energy neutrino experiment above the energy range of ice cube, and I hope I've convinced you that it's an interesting thing to do. But if it was easy, it would have been done by now. I always think about that like if it's easy, someone would have done it. And so it turns out that this is the reason it's hard. It's hard because neutrinos are weakly interacting. The same property that makes it so that neutrinos are perfect messenger particles for distant sources, right, means that they'll just basically zip right through the Earth most of the time and you'll never see them. So what that means is you have to build a really big detector. So this is what IceCube did. But it turns out that at these high energies, IceCube is just too small. A cubic kilometer is not enough volume to instrument to see the highest energy neutrinos. And so I would argue that that's where you have to get creative. And that's kind of the fun part, at least for me, is figuring out, okay, here's this interesting science question. If we could build a experiment that goes to the highest energies for neutrinos, how would you do that? Okay, so this is what we're going to do. We are doing two different things. So one is putting a bunch of radio antennas on a balloon. Okay, so why would you do this? So neutrinos interact in, what do you need to see a lot of neutrino interactions? You need a dense detector, because the more stuff you have in your detector for it to interact with, the higher the chance of interaction. And you need a big detector. So in our case, we're actually using the Antarctic ice, just like IceCube is, as our detector, meaning the neutrino makes a particle shower. That's what's shown on the left here. The neutrino makes a particle shower in the ice, and then that particle shower gives off radiation. But one of the tricks that we're using to go to the highest energies is that instead of looking for the optical light that IceCube is looking for from these showers, we're actually looking for the radio emission that these showers make. And the reason we're doing that is twofold. One is that turns out ice is really transparent to radio waves. And so you can instrument a large volume of ice more efficiently with a radio antenna array than you can with an optical array, because you can put your detectors farther apart, right? The other reason we're looking for radio waves is because it turns out, due to some underlying physics, that because that at the highest energies, there's actually more power in radio than there is in optical. So if you want to like hit the sweet spot and measure the high energy neutrinos, there's actually a brighter signal in radio. So it's kind of the coincidence that it's a brighter signal in radio, and you can instrument larger volumes with radio detectors than you can with optical detectors. So we're building two experiments. One is a balloon experiment. You hang a bunch of antennas from a large balloon and fly it over Antarctica, and you look down at the Antarctic continent for neutrino interactions in the ice. And then the other is an in-ice detector, where you do something very similar. It's kind of like a mix between the balloon radio technique and the IceCube technique, where you put antennas into the ice, spaced farther apart to instrument more volume. And then you look for neutrinos that way. So those two techniques, where you build something that looks, that's on a balloon and looks down at the ice, compared to where you build something in the ground, turns out that they're not exactly the same. They're complementary. So you actually get different physics with each one. And that's because we're back to this same plot of energy. That's because the ground-based experiments that I'm working on cover the energy range shown in blue, and the balloon experiments cover the energy range in green. So you really need both to cover the energy range all the way up. And the reason they cover different energy ranges is because you can actually imagine if you fly an antenna on a balloon, that antenna is really far away from your neutrino interaction because the balloon is flying at 40 kilometers. And so the average neutrino interaction is many hundreds of kilometers away from you because you're kind of looking out and down. That means the signal had to be really bright to get to you, right? Otherwise it would be too small. And what does it mean to have a really bright signal? It means that the shower had to be very energetic. So ultimately it means the balloon experiment, we call it a higher energy threshold, meaning it's only sensitive to the very highest energies. The flip side is that the balloon can see a lot of ice. I mean, it's a very efficient way to instrument a lot of ice, is to fly something 40 kilometers over the ice and build sort of a telescope that looks out at the whole ice. So that's the sort of flip side. So that's where the two instruments sit. Okay, so I'll talk about the balloon mission first. So the balloon mission is called PUEO, the Payload for Ultra High Energy Observations. I think it's the most beautiful experiment I've worked on. I've worked on a lot of good looking experiments, but this one has a lot going on to look at. It's a NASA long duration balloon mission. Basically due to technology advancements that my group and others have worked on over the last 10 years, we've figured out how to make a factor of, I put a factor of 10 on the slide, but it's really probably a factor of 30 or 40 improvement over the current best sensitivity that has been achieved at these energies. And the way we did this was basically building a better trigger system. So what is a trigger system? A trigger system, it turns out that you have to build your detector in a way so that when a neutrino signal passes by, it guesses really well that a neutrino signal passes by. You can't record data all the time because the data rate would be way too high. So you have to have something built into the hardware that sort of has some logic on it that allows you to only record data at the right times. So how efficient you are at guessing what the right time is determines the sensitivity of your experiment. This is common across all particle physics experiments, right? Like if you were at the LHC at CERN, colliding high energy particles, they have an even harder problem than I do. They have to build a really efficient, it's called a trigger, to figure out when to record data. So we figured out basically a much more efficient way to pick when we record data. And that's what allowed the advancement here. Okay, so there's the main instrument, that's this part on the top with a dual polarization beamforming trigger. That's the kind of trigger that we're flying. And then we're also adding this low frequency instrument. So low frequency means bigger antennas. We added this low frequency instrument because it turns out that a previous experiment that this is built on had observed a lot of cosmic ray events. I've only talked about neutrinos, but we can also see a lot of cosmic rays with this experiment, and we wanted to add some low frequency sensitivity to boost our cosmic ray sensitivity. Okay, then we have all the rest of the stuff you need to fly a balloon for 30 days and take data. So we have triply redundant storage, command and control, a navigation suite, housekeeping and environmental sensor system, and all of that. It's like yeah. So we were selected for an Astrophysics Pioneers mission by NASA a little over 2 years ago. I'm trying to think, I kind of lost track of the number of years during the pandemic, but a little over 2 years ago. We were very fortunate that NASA decided that this was a niche that needed to be filled. So NASA is really great at building bigger missions, bigger satellite missions. And it's also really great at doing smaller R&D projects. But there was kind of this gap at NASA in the $10 to $20 million range, where no matter what platform you wanted to fly on, whether it was a small satellite, a balloon, a CubeSat, a rocket, or put something on the space station, it was hard to get that project funded. So they put out this new call called the Pioneers in Astrophysics program, and they selected 4 initial missions. It's us and 3 small satellites. So the other ones are small satellites trying desperately to stay under the $20 million cost cap to launch a satellite into space, which is kind of incredible that they can do that. The other missions are super cool also. There's an exoplanet mission, an X-ray mission, and a UV mission. And all 4 missions passed the gate review, which I think was to the surprise of NASA. I think they assumed that someone would fall off, but now they're stuck paying for all of our missions, which is great. and we've been approved to proceed to implementation. So we're scheduled to fly from Antarctica in 2024, which is coming up fast. In about a year from now, we will have built a fully completed payload and instrument in a brand new high bay facility at UChicago and get it ready to ship to Antarctica. So what is PUEO's top level science question? I think I talked about this already, but we're basically trying to understand what is the nature and cosmic distribution of astrophysical accelerators that produce the highest energy particles in the universe. And this is just a picture of our PUEO team at our first collaboration meeting. And this picture is very dated now, right? Because you can see a third of our collaborations on Zoom and half our collaboration is in person. So you can probably guess exactly when this was. It was, about a year ago, right? Where everyone is masked and it's our first in-person meeting after the pandemic, but still not everybody came in person. We're having another meeting soon, and I think it'll be a little more. I think everyone will come, which will be great. But we have 7 US institutions and a few international partners on the PUEO mission. And, I just put a picture here of from the launch of a previous instrument that actually looks a lot like PUEO. It's called ANITA, and that's the instrument that this was sort of built on. But our technology advancement allowed us to get a lot better sensitivity. So this is a helium balloon. It's a zero pressure helium balloon, meaning it's not closed, it's open to the environment. And down here in the orange, that's the parachute for when ultimately we cut down and fall to the ground. The launch vehicle currently has the payload on it in this picture. And essentially what happens is, they pull the pin, the balloon starts rising. This picture was taken after the balloon started rising. And then they drive the truck around on the runway so that they match the speed and direction of the balloon. And then at just the right time, when everything gets just taut enough, they reverse the truck, pull the pin, and then the payload flies off. Well, okay, hopefully the payload gently leaves the truck, right? And then everything rises up to 40 kilometers. Okay, so that's PUEO, and we are on track to launch in 2024, but that is what's keeping me up at night right now, research-wise. The other thing that our group is working on is called the Radio Neutrino Observatory in Greenland. This is a ground-based experiment at that place called Summit Station in Greenland I talked about on the first slide. And it takes advantage of similar technology advancements as PUEO. So the trick we're playing to make a better trigger on PUEO also works here. So this is a much more sensitive ground-based detector than anyone has tried to build before. We secured funding mostly actually through Europe, through our European partners. A lot from Belgium and Germany for the most part. We also have Swedish collaborators, but most of the hardware money is coming from Belgium. And we're planning to build 35 stations 35 sets of antennas up at Summit Station in Greenland. Somehow through, I don't know, dumb luck or magic, we managed to deploy our first instrumentation in 2021, right in the pandemic. And then we have 7 complete stations running well right now, and we are going up this year for a calibration season, and then we'll go back and continue to deploy in 2024. This is what an RNOG station looks like in cartoon form. So there's some antennas near the surface of the ice, and then there's another set of antennas down about 100 meters below the surface of the ice. The reason you want to get below the surface of the ice in our case is because the surface of the ice for the first 100 meters, it's called the firn. It's a slow compactification from snow to ice. And we just want to get out of that transition into the deep ice. You get much more clear signals if you do that. And this is just a cartoon of a neutrino event with a particle shower making those radio waves we look for. And here's a picture of our collaboration meeting again in Chicago just last spring also. One of the kind of interesting things for RNOG is that we need to drill holes 100 meters into the ice, and we need to do it quickly and efficiently. But unlike most people who drill holes 100 meters into ice, we don't care about recovering the ice core. Okay, so we don't care if it chips up into whatever they need to do to get it out the hole. We just want to get 100-meter holes drilled at relatively wide diameters pretty quickly. So we actually worked with the British Antarctic Survey, BAS, and developed a new drill with them, the Big Raid drill that we are using. And it's an auger drill, meaning it just has a bit that turns and it chips up the ice. And we've managed, and we built a big tent, so that's on the lower right, so you can work a little bit better. And yeah, the drilling, it turns out, is one of the major technological challenges of doing this. You wouldn't have thought it, but somehow it is. And after we drill the holes into the ice, we deploy the stations. So we actually designed this little shed to be towed by a snow machine, which was the major design constraint for the shed, is like, how can we build this thing to withstand 100-mile-an-hour winds and weigh less than 500 pounds? So that was kind of a fun project to work on with grad students and engineers. And this is, sometimes it's pulled by people if it gets stuck someplace, but usually it's pulled by a snow machine. These are our antennas that go near the surface in trenches, and then these are our antennas that go down the holes. And we turned on our detector, and the first thing we see is events that, to my eye, this is an event display. So this is what sort of the data looks like from one instrument. To me, actually, this looks kind of close to a neutrino event. So if a neutrino happened in our detector, it would make a really snappy signal like this. But in this case, it's a snowmobile. So this is also made by snowmobiles driving over the surface of the snow. And okay, to first order, it looks sort of like a neutrino, but I can imagine 10 different cuts. You could easily separate neutrinos from this kind of signal. So this isn't really a problem for us. It's just, it triggers our instrument because we're looking for neutrino-like things. And it turns out that snowmobiles make somewhat neutrino-like things. And then it turns out we also built our own calibration sources that intentionally make neutrino-like signals so that we can test out all kinds of things with our detector in real time. It's really important to have a calibrated instrument so you know what you're looking at. And I won't go into this too much, but we can successfully sort of do first analysis with our calibration data. The data acquisition system was almost all built at UChicago, and I kind of find it amusing that you know, almost all the boards on the right are home built by us and collaborators as well. And it's, you know, it's a pretty custom system, and you have to have a lot of pieces working correctly. And then the funny part is, at the end of the day, you put the lid on it on the picture on the left. That's the lid on the thing on the right. And then you know, go to Home Depot and you buy some foam, and then you know, put it in a box and you just leave it out on the Arctic plateau. And then it takes data. So I just want to leave you with a summary, and then we can, you know, chat for a while. I think, you know, it's been an exciting few years. And things have advanced relatively quickly. It's almost like when it rains, it pours. So we had one experiment get approved and funded, and then the second experiment get approved and funded, because they're complementary, right? But what that means is right now we are working to get both of these up and running and out the door, so that we can reap the benefits scientifically over the next few years. Both of these projects are under construction, and I am hopeful that at least one of these projects will discover ultra high energy neutrinos. And ultimately, we hope to do neutrino astronomy with these events, not just discover one or two events at the highest energies, but build a real observatory that can identify sources and figure out what is the physics that's driving. Okay, so thank you.
Abby, thank you so much. This is really exciting work. What we'd like to do is open up to questions. So if you have a question, there's a way to raise your hand if you are Zoom savvy with the reactions button down at the bottom, or if you're not savvy enough to know how to raise your hand, just unmute yourself and speak up if you have a question, please.
Well, I have
Josh,
one.
I think, yeah,
I'm no shortage of questions.
I was going to say, I can also make up the 5 most common questions I get and answer them, because that's.
Oh, there you go. Yeah,
Yeah.
maybe that's what we do, an FAQ portion and then a further Q&A portion.
No, you should ask Josh.
But well, one question I have actually is more about neutrinos more broadly. So they, as I understand, right, as you explained, they're, you know, the highest energy particles in the universe, and they do have mass, which means that they can't exactly travel at the speed of light. So are there, relatively speaking, like slower neutrinos, and what might be the benefit of isolating those compared to the high energy ones?
Yeah, so there are very high energy neutrinos. That's what we're going for. It actually turns out that your question, so the slowest neutrinos, meaning the lowest energy neutrinos, a population of slow neutrinos that are non-relativistic now is neutrinos left over from the Big Bang, actually. So very early in the universe was like this bath of all kinds of particles, and then slowly over time, as the universe expanded and cooled, the different types of particles could decouple from the plasma. Does that make sense? And then there's sort of this bath of particles around us. So this is how the cosmic microwave background, this is what the cosmic microwave background is. It's the photons left over, it's the light left over from the Big Bang, essentially. It was photons that were rattling around in the plasma in the early universe, and then about 400,000 years after the Big Bang, the universe had cooled enough that those photons, that electrons and protons combine to form neutral hydrogen, and then those photons come to us today. So that's the CMB. It turns out there's actually a cosmic neutrino background that was released earlier in the cosmic history. The energy of those neutrinos is like an one eV. So if you looked at the plots I was showing, like we're looking for particles up to 10 to the 20 eV, but there are particles all the way down at the very low energies that are left over from the Big Bang. If you could measure those, you'd get a Nobel Prize. That would be incredible. So if
I'll get right on it.
Yeah. I don't know how to do it either. Otherwise, I would be building that experiment. But the reason they're so hard to measure is because the chance that the neutrino interacts with your detector goes up as a function of energy. It's called the cross section. So the probability of interaction for very low energy neutrinos is just so low that even though we can see the effects of the cosmic neutrino background on things like structure formation, no one has yet figured out how to build a detector in a lab to actually measure it. Yeah. People try. People have tried. People are trying.
Abby, we've had some interesting questions coming in on the chat, and I think that you may have inadvertently answered the first one there, which was
good.
How can neutrinos be used to investigate the early universe before photons were released after?
I did already answer that one.
Yeah,
neutrinos are super cool. So it turns out that cosmic neutrino background is super interesting because the number of types of neutrinos and their mass determines how structure is formed later in the universe. So you can turn that around and go measure, use something called, you can survey galaxies across cosmic time and turn that around and back out how many types of neutrinos and the mass of the neutrinos from that. Okay, that was...
David Vargo asked about what makes a detector dense.
Okay, so you need a dense detector for neutrinos to interact. And what I mean by that is you just need, it's the number of it's just the number of atoms in that detector. So like something that is heavier, that's what I mean by dense, is heavier. But to detect radio waves, you need, so the neutrino interacts, the chance that it interacts goes up if your detector is more dense, if it's heavier per unit volume. Then you need a way to measure the effects of the particle. You need a way to measure the radio emission that's made from the particle shower. In order to do that, you need to have a material that's radio transparent, right? Because so let's say like metal is dense. Metal is not radio transparent, it's a conductor. So as soon as a neutrino interacts in metal, it doesn't make any radio waves you could go see, right? You need something called a dielectric, right? And you need something that's radio transparent. And then you stick an antenna to measure the radio waves. So it's kind of two different things you need, actually.
Thank you. Audrey Scott has an interesting question more
on
Yeah, what has been the most challenging piece about working with NASA, and what expectations are on you as part of that?
Right. So this is the first time I've been the PI of a NASA mission. So it's been, so I would say the biggest challenge has been that it's a new program. That's the biggest challenge, actually, that the program that we are funded under, this Pioneers program, is a new program. And we were in the inaugural class of 4. And the program is run out of the Small Satellite Project Office. Okay, we are not a small satellite. So there's a separate project office called the Balloon Project Office that we are not run out of. And so I would say that has actually been the biggest challenge, that like all of the reviews and all of the, discussion and are set up with building a satellite in mind, and building a balloon just has very different, well, sometimes similar and sometimes different constraints. So that's been, at times it's kind of felt like we're trying to shove a square peg into a round hole. But
Right.
Usually what happens is they make the hole a little more square, and then we move forward.
Nice. So Abby, I've got a ton of questions to ask. So it turns out, because of my association with Chicago back in the 80s and 90s, I spent a lot of time working in the U.S. Antarctic program. So I know the South Pole and long duration balloon programs really well. My first question is, have you been to Antarctica yet?
Yeah. So if no one was gonna ask questions and then you were gonna ask me what are the top 5 questions you might get, the first one would be, how do you get to Antarctica? So I've been to Antarctica. I've been on 2 balloon missions in Antarctica. I also have worked on a telescope at the South Pole. So I've been to South Pole, I think 4 or 5 times. And then I've been to Greenland, so Summit Station, to start working on that experiment. I've been there twice. As a graduate student, it was one of the things that I just loved it. I loved working in the field. I still love it. Now I have a lot more constraints, so it makes it harder. But as a graduate student, it was just incredible. Scientifically, working in the field is like no other, in the sense that you're often working side by side, long hours with your advisor. And it's like the amount of osmosis per day is, you just don't get that at home, right? And so you don't get that kind of interaction. And then you go to the field and you just learn a lot. So scientifically, it's amazing. Personally, going to these places it's pretty incredible. It's a pretty cool experience. Yeah.
Biggest surprise
about Antarctica?
Yeah.
Oh, that's so funny, because it's been so long. I have this, I can't even think of a surprise, because I know exactly what it's going to be like when I go. Well, okay. I think one thing that's really nice about it doesn't feel as, I don't know, somehow it doesn't feel as far away as it sounds. Maybe that sounds odd to say, but you fly to New Zealand, which is a long flight, and then you're in New Zealand and you wait for a plane to McMurdo, and then if you're going on to South Pole, you wait for a plane to South Pole. But somehow there's still internet, and there's still, I don't know, there's just all the comforts of home. It's a really nice place to work. In McMurdo, there's like a gym and a cafeteria and movie night and a bar. It doesn't feel, in some ways it feels very remote and serious, and in other ways it feels like it might as well, McMurdo in particular, that's the main US base. It might as well be sort of a mining town in South Dakota in some way.
Yeah. Thank you for the thoughts on Antarctica. If you're up for a few more questions, we have some in the chat. Timothy Lyman is asking if there's still evidence for a 4th neutrino.
Yeah. Okay. So there's been a fair number of accelerator and reactor-based neutrino experiments that people have built to measure neutrinos of different flavors and different types, and look at neutrino oscillations. You can it's pretty cool, actually. You can, at a place like Fermilab, you can build something that makes a beam of neutrinos. And you do this by colliding protons with a target that makes muons, and then muons and muon neutrinos. And then you stop the muons, or you bend them away with a magnet. And then you're left with a neutrino beam. And then you can do all kinds of things with this neutrino beam and measure the heck out of it. So if you do that, there's been quite a few experiments who've seen a fair number of anomalies. I assume this is what Timothy's referencing to, a fair number of anomalies where like the oscillations didn't quite look the way they thought they should. And one way to explain this is with a fourth neutrino, often called a sterile neutrino, basically a fourth species of neutrino that would have to behave slightly differently, but would oscillate with the other ones. Those anomalies still persist. They are not all consistent with each other. Does that make sense? It's not like they all paint one picture that we can then go look for, a fourth neutrino that fits this bucket. My understanding is like there's different anomalies in different places, and there are ways to try to combine them to understand what they're telling us, but it's not like there's one clear picture that comes out of that. I will also say, because I tend to look at things from like the cosmology perspective or the astrophysics perspective. From cosmology, there's no evidence for a fourth neutrino. So from cosmology, from that cosmic neutrino background and looking at its effect on the plasma in the early universe and also later on structure formation, you can count what we call the number of relativistic species. So you can count how many particles are neutrino-like in the early universe, and the answer always comes up 3. So from everything we've done in cosmology, it really looks like there are 3 neutrino-like types of particles in the early universe. But we keep trying to measure that more and more precise. This is one of the goals of future experiments. Try to see if there's evidence for a fourth neutrino. That would be incredible if there was.
One more question that's a little more on the instrumentation side is from Travis Dietz, who's one of our board members on the Space Network as well. What other ionizing radiation or physical phenomena are you concerned about as interference sources?
Yep. So we worry a lot about background. That's basically how I would characterize that question, is like, okay, so you're going to measure neutrinos, but ultimately there's other stuff that might look like a neutrino. So there's a few big things. One is cosmic rays, actually. So cosmic rays make short blips of radio waves when they create air showers in the atmosphere. Those look pretty neutrino-like, but they are distinguishable in our data based on direction. I mean, that's, you point it up versus point it down, basically, and you can distinguish that. The big background that we battle is actually man-made noise. So, it's somebody turns on a snowmobile and drives over our experiment. And yes, snowmobile signals look different in general from neutrino signals in detail, but it's possible that we could get tricked, right? That like somebody will make a signal that looks very neutrino-like. And so we try to estimate this. We try to look at, what are the distributions of events from different kinds of things and like extrapolate to guess how many would be neutrino-like. We call that a background estimate, and then we're kind of stuck with it. But yeah, there are other things that could, in principle, on the sort of single event scale, make neutrino-like events. But I guess I would counter that by saying that's only a problem in the discovery regime, which I'm hoping to get past soon, right? As soon as you have tens or hundreds of events, it doesn't really matter if one actually came from a snowmobile, right?
Right.
As much. Yeah.
One question I'd like to end on came also from Audrey Scott. So, the Space Network is a way for people who are interested in the science of space and astrophysics, as well as people who are working in the space industry. We're really excited about the cross-fertilization that we're seeing in this group. And so this question kind of ties directly to that. Is there any interaction that your science experiment or others have with commercial industry, and is there more room for collaboration there?
Yeah. So for us in particular, I would say two things. One is we ultimately, I mean, the earlier question from Audrey, my answer was, we're a balloon trying to fit in a satellite shell, which is difficult, or a satellite bucket, which is difficult at NASA. But the reality is there's a lot in common between building a payload that goes on a spacecraft, a satellite, and building a payload that goes on a balloon. So we use a lot of vendors that you would use for aerospace, right? And we work with a lot of, it turns out most of the people who we buy things from for our instrument or work with to design pieces of our instrument, right, are either defense contractors and or aerospace contractors. But usually that's kind of like in a one-off relationship where we find someone who has something similar and then we call them and say, well, can you make this other thing, that's close. The other way, so that's not a lot of interaction. The other way I would say that my group has had some interaction is I would say like over half of the undergrads who've worked in my lab are in aerospace. They come to my lab, even though I do particle astrophysics and I am a physicist and an astronomer, and I don't really know much about aerospace engineering. All of the students at UChicago who want to do aerospace engineering, they seem to come to my lab. Partly because we don't have aerospace engineering directly, right? And so it's actually kind of fun to send them off, and they want to go to grad school, and they're getting masters and PhDs, or ultimately going off to internships at SpaceX or places like that. My most recent undergrad now is a job at Blue Origin. So so I would say that is one connection for sure.
Yeah. Oh, Abby, that is awesome. So be sure, it's a perfect segue here to wrap up and do one more advertising pitch for the U of C Space Network, which is make sure all those students in your lab know about our space network too, because one of the things that is important to us is to connect alumni and current students to provide mentorship in some of those paths into the space industry. Abby, thank you so much. This has been such an exciting and informative talk. I would love to geek out some more about Antarctica, but we'll have to find another time for that. It is time to wrap up. And so I would like to thank everybody for your participation in the conversation today. Our next Space Talk is coming up on April 23rd. It's going to feature one of our Space Network board members, Jerry McIntyre, who is an MBA 21, is currently the VP for legal at a company called Orbit Fab, which is a gas stations in space company. And he is going to talk about the legal challenges of being a startup space company. So please join us. I've known Jerry a long time. I've worked with him. He's a great guy and a great speaker, and definitely encourage you to come to that. Josh, I know that you've got a few final items to wrap up with, so let me turn it over to you to bookend our talk today.
I appreciate it, Dave, and I appreciate everyone here who joined us for this hour of lunchtime learning. Appreciate you, Professor Vieregg, for taking us on this journey to Antarctica. Dave captured really a lot of the highlights. I dropped in the chat where you can learn more about Professor Vieregg's research at astrophysics.uchicago.edu. I encourage you to join us in a few weeks for our next Space Talk. You can connect with the UChicago Space Network on LinkedIn and subscribe to the UChicago Space Network newsletter. I'll also send those in a follow-up email to everyone here and who signed up. Once again, please feel free to reach out to us anytime. This is a tremendously generous and passionate group. Have a great afternoon and weekend, friends.